Hello everyone. In this lecture I would like to discuss the notion of the electric field. Now this lesson is going to be primarily directed towards undergraduate students. So if you have enjoyed and learned from my earlier lectures on electrodynamics, you may want to revisit the notion of electric field through this lecture. So, why do we need the concept of a field? Now, there are certain limitations. If you want to use the Coulomb's law, only the Coulomb's law, then we find that there are certain constraints within which the Coulomb's law is applicable. Because the Coulomb's law is based on two assumptions. The first assumption is that the charges are localized and they are stationary. We have stationary localized charges. And the second assumption is that all the charges are point charges. So because of these two assumptions, the Coulomb's law by itself, it has got very limited scope. So some of those limitations of Coulomb's law are it ignores how the force between the charges is transmitted. So it just says that the force, there are two charges which are separated by a distance, and there is going to be some kind of a force between them. But how exactly is the force conveyed from one charge to another charge? That is ignored by the Coulomb's law. It looks at force as what is called as an action at a distance, similar to the gravitational force. Then it also overlooks the significance of the intervening space, so space between the two charges. What role does it play in transmitting the force between one charge and another charge? The Coulomb's law, it overlooks the significance of that space. So the experimental observations, they suggest that there is indeed a finite speed for such electromagnetic interactions, and this speed turns out to be equal to 299792458 meters per second, which is nothing but the speed of light. So let us say I am having two charges, Q1 and Q2, in vacuum. Initially they are at positions O and A. So charge Q1 is at A and charge Q2 is at position O, and these two are separated by some distance d. Then suppose I move this charge Q1 from point A, I move it to point B. Then it's going to take a certain amount of time before the second charge Q2, before it feels that change. The time that it's going to take is going to be equal to d by c. D is the distance, the separation distance between them, and c is the speed of light, the speed at which the interaction is, the information regarding this interaction is carried from one charge to another charge. Okay, so this change in the position of Q1 will be felt by Q2 only after a time d by c has elapsed, and it will not happen instantaneously. So to understand this, let us draw inspiration from the case of gravity, which is already familiar to us. So all objects near the earth we know will be attracted due to the gravitational force, and if the earth were suddenly to vanish, all near objects will not feel any gravitational force. Okay, so let's look at that. So let us say that I have an object of mass m1 which is somewhere near the earth. Okay, because we all know that because of the earth's gravitational pull, this mass m1 is going to experience some kind of a force, and that force we call it as f1, and we know how to calculate that force, f1. Now another mass, if I have let's say at some other location near the earth's surface, let's say that mass is m2, that mass m2 is also going to feel some force which is going to be directed towards the earth. To be more specific, this f1 and f2, these two forces are directed towards the center of the earth, so that's why they are called as central forces. So now suppose, hypothetically speaking, let's imagine that the earth has suddenly vanished. Let's say by some means you are able to make the earth vanish. Then what is going to happen is this mass m1 and mass m2, they are not going to feel any kind of a force which is attracting them anywhere. Okay, so if mass m1 is at rest, it will continue to remain at rest. If mass m2 is in motion, is in uniform motion, it will continue to move in a straight line. So it seems as if the very presence of the earth has altered the properties of the surrounding space. So what I mean by that is, these two masses, they are in some space. Here also they are in the same space, but there is a difference between these two cases. Here these two masses, they don't feel a force, but here they feel a force, and the difference between these two is the presence of the earth. So as if the very fact that the earth is present, it has somehow modified the space which surrounds the earth, and these two masses, they're basically responding to this modification in the space. Okay, so the earth seems to have spread its field of influence in the surrounding space. So there is some kind of a field of influence that the earth seems to have generated in the surrounding space, and this space seems to have acquired a physical property. So this field of influence which you're talking about, it seems to have imparted some kind of a physical property to the given space. So we call this property as the earth's gravitational field. Okay, and in general, such a field may be phenomenologically, it may be characterized in general in this way. We can measure the field at a place in terms of the force experienced by an object. So field is defined more generally as the force experienced by an object due to the field divided by the property of matter that responds to the field. So this is a general expression which is applicable to the electric field as well as the gravitational field as well. So the earth's gravitational field is the force experienced by the object due to that field, that force, let's say that is F. And what is the property of matter that responds to that field? So matter has got many properties such as mass and charge. So out of these properties, mass is the property which responds to the gravitational field. So force, the gravitational force divided by the mass of the object, that is what we call as the earth's gravitational field. And you all will be able to recognize that this small g is nothing but the acceleration due to gravity. So the g, that is acceleration due to gravity, which is actually the earth's gravitational field, it depends only on the position. It only depends on the position of the object. You would have learned this in your lower classes, that as the position of the object, as you go far and far away from the earth's surface, the acceleration due to gravity, it decreases. Again, as you suppose dig deeper into the earth's surface and keep going towards the center of the earth, again the acceleration due to gravity will decrease. So the acceleration due to gravity is going to be maximum at the surface of the earth. So it means another way of looking at it is the acceleration due to gravity or the gravitational field of the earth, it depends only on the position. Okay, so this position, I'm just in general I'm writing it as r here, but if it's Cartesian coordinates, then you could just write it as x, y, z. If it is spherical polar coordinates, you could express this as r, theta and phi. So there is an alternate picture of gravity emerges. So what is the alternate picture? The alternate picture is the earth, it sets up what is called as a gravitational field in the surrounding space. So it is the earth which is the prime mover here. The presence of the earth, it modifies the surroundings and creates what is called as a gravitational field. So now any object which is any particle which is placed in this field, please pardon the error here, any particle which is placed, it's not placed, the word not should not be here. Any particle which is placed in this field, it experiences a force which is proportional to its mass. So the earth sets up the gravitational field, and when a particle of certain mass m is placed in this gravitational field, it will experience a force, and that force is going to be proportional to its mass. So in general, okay, we could define something as a field. So what is a field? Field is any physical quantity which is specified at all points in space for all time. That means any physical quantity which is known to us and which is defined for all points in space at all times, that is what we call as a field. So field could be a scalar field, for example a temperature field. For instance, the temperature of the room which you are right now in, at different positions, at different locations in the room, the temperature is going to be slightly different. So if you could map out the temperature at different positions at all times, then that becomes a temperature field. Then we could have a velocity field. Example of a vector field is a velocity field in a fluid. So in a fluid which is a liquid which is flowing, so in that liquid the different points in the liquid will have different velocity components. So if you are able to map out these velocities at all points of time, then you get what is called as the velocity field. So now let us apply these ideas and try to understand what an electric field does. So if you go back here, so what happens here is there is a property of matter which responds to this field, okay. So and it basically experiences a force due to that field, okay. So that force divided by the property is nothing but the field. So we'll keep this idea and move forward here. So what is an electric field? Electric field is the field that surrounds a stationary charged particle, okay. To put it simply, electric field is simply the field. And what is the field? We have defined a field earlier here. What is the field? Field is any physical quantity specified at all points in space for all times. So an electric field is a quantity which is specified at all points in space at all times, okay, and which surrounds a stationary charged particle. Now because it's a stationary charged particle, the time factor is not going to, it's going to be, that field itself is going to be stationary at all times. What happens if the charge is moving? If the charge is moving, it gives rise to both electric and the so-called magnetic fields. Of course, the magnetic field is a consequence of relativity, but I'll not really go into that right now. So in terms of the electric field, the Coulombic force between two charges may be visualized in the following manner. So let's say I have a charge Q. This charge Q sets up an electric field in its vicinity. It's similar to the gravitational field that we have discussed some time back. In gravitational field, what happens is a mass like the earth, it sets up a gravitational field. So in a similar way, a charge Q sets up an electric field in its vicinity. And in gravitational field, what happens is, now if I place another mass in the gravitational field, it is going to experience a force. So in a similar way, if I have a test charge and I place it at some position r with respect to Q, then this test charge is going to experience a force, and this force is given by force is equal to charge into the electric field. So how do I get this expression? We get this expression from that general general relation between field, force and the property of matter. So field is equal to force by property. That means force is equal to field times property. So in case of electric field, the property is charge, and we have the electric field and we have the force. So the force experience will be charge times the electric field. Okay, so the force experienced is going to be charge times the electric field. So from Coulomb's law, the force between these two charges, okay, the force between two charges according to Coulomb's law is basically 1 by 4 pi epsilon naught, the product of the charges divided by the square of the distance between them, times the unit vector, okay. This is equation 1 and this is equation number 2. So if you compare these two equations, then we obtain, that is, this side must be equal to this. So as a result, this test charge will get cancelled out, which is good news for us, because the electric field should depend only on the charge which sets up the electric field. It should not depend on the test charge. So because the test charge has got cancelled out, that means it reassures us that, okay, we are on the right track. So this gives us that the electric field due to this charge Q is given as this. Okay, so this idea that we have here, the Coulombic force, the visualization of the Coulombic force. So there is a small animation here which I'd like to show you. So let us say I have this charge, okay. So we have a small charge Q, okay. This small charge Q, it exists at some point in space. It sets up an electric field. That means it sets up a region of influence. So this is, I'm trying to visualize, I've used this color to visualize that region of influence. It's going to be radially, it's going to be symmetric. So it's got spherical symmetry. So it's going to be the same value and all at equal radial directions. So it sets up an electric field. So this is the electric field which it sets up. So now, just a second, yeah. So it sets up the electric field here. Then now let's say I place at some point, okay, at some point which is at a position r, let's say I place it sets up some electric field E, okay. So this charge Q, it modifies its surroundings, and at some point which is at a separation of r from this charge, it sets up an electric field, and this electric field is given by this expression. Now let's say I place a test charge here. So what is going to happen to a test charge? The test charge is going to experience a force, okay, and the force that is experienced by the test charge is F, okay. So this is basically the visualization of the Coulombic force in terms of the electric field. So it's the charge at the center which sets up the charge at the center, which first sets up the electric field, and then when I place another charge over here, it responds to the electric field by experiencing a force. So nowadays we could have a phenomenological definition of the electric field at any point. Okay, so what you can do is, suppose I want to sample the electric field at any point, then what you do is we measure the force experienced by a test charge q which is placed at that point, and you calculate the electric field simply as E divided by E is equal to F by Q. So you can understand it this way. So let us say I have a test charge. So this is some region, okay, this is some region, you can see that it is shaded. That means there could be some kind of an electric field within this region. What is causing that electric field? Right now we are not really bothered. Okay, the electric field could be caused by a single charge, or it could be caused by a collection of charges, or it could be caused by a distribution of charges. So we really are not interested in knowing the origin of the electric field, but we just know that there is some kind of an electric field in this region. So we want to find out, we want to know what is the electric field in this region. So how do we do that? So for that we have this phenomenological definition. So what we do is we take a test charge and we place it at some position. So we have a test charge q which we place it over here, and then we find that the test charge, it experiences some kind of a force. Okay, the test charge experiences some kind of a force F. Then using this force we can find out what is the electric field. So using this formula, so all we need to do is whatever force has been experienced by the test charge, you divide it by the charge, that is going to give us the electric field at that point. Without actually knowing what is causing the electric field, we are, in a sense, we are sampling the field at any one point without actually bothering about what is actually causing that field. So but then there is a problem here. The problem is there is a chance that the test charge, it might disturb the system itself. So let's say I have a charge whose a charge of, let's say, half a coulomb, and let's say which is placed at some position, and let's say I use a test charge of 1 coulomb. So definitely this 1 coulomb is going to be dominating over this half a coulomb charge, and it might, push it afar. So as a result, what is happening is the electric field which I will be measuring at the point where I place the test charge, that electric field is not going to be accurate because I have disturbed the system. So in order to ensure that I do not disturb the system, what we do is the test charge that we use, we make it vanishingly small. That means this equation number 4, we just modify this, and we have that condition that this ratio, okay, we evaluate this ratio as q tends to 0. Okay, so when we do that, whatever value you get and of this ratio and this limit, that is going to be the electric field. Now this is understandable. Let's say I want to find out gravitational field near the Earth's surface. Okay, so for that I would be using a small object. So any small object will do, which is because whose mass is negligible compared to the mass of the Earth, and that because actually speaking, what happens according to Newton's third law, any object, let's say for example myself, I have a certain amount of mass. The force of gravity between me and the Earth is mutual. That means whatever is the force that the Earth is exerting at me is also the same force which I am exerting on the Earth. But we don't see the Earth accelerating towards me. Okay, I see only myself accelerating towards the Earth. Suppose I am in free fall, only I will be accelerating towards the Earth. The reason for that is the acceleration that I experience is going to be very large compared to the acceleration which the Earth is going to experience. The force is going to be same. The force is going to be just the same in both the cases. Okay, but the acceleration that I experience is going to be different. Okay, so what will happen if instead of using me as a test mass, what if I use, let's say, something like the moon itself as a test mass? So in that case, what will happen is the mass of the moon is comparable to the mass of the Earth. So in that case, there is going to be the position of the Earth is going to change. So I will not really get an accurate measurement of the field. So that's the reason why, in a similar in using similar logic here, we cannot afford to make the test charge as large as we want. It has to be made vanishingly small. It cannot be 0 also, because if it is 0, then it becomes a neutral particle. It will not experience any force due to the electric field. So it should be very small, but not exactly 0. So that's why we have modified this equation number 4 and wrote it like this. Okay, so what is the electric field due to a point charge? We have already seen, but that was with respect to the point charge itself. Now a more formal expression for this is if I have a fixed origin. So I have a fixed origin. So this was the x, y, and z coordinate, the coordinate axis. This is the origin. So I have a charge q here, which is at a position r prime. I want to find out what is the field that is produced by this charge at this position r. Then what is the separation vector? The separation vector between the charge and the field is r minus r prime. Then the electric field at this point is going to be E, and this electric field, you can work this out, this electric field will be 1 by 4 pi epsilon naught q r minus r prime divided by modulus r minus r prime to the power 3. Now how did this 3 come here? It was supposed to be 1 by r square. That is because I have also incorporated the unit vector here, the unit vector along this direction. Along this direction, the unit vector is r minus r prime divided by modulus r minus r prime, and already we had q divided by modulus r minus r prime square, that square and the modulus r minus r prime from the denominator of the unit vector. When you bring them together, it is, we'll get a power 3 here, but otherwise this is not a cubic inverse cube equation, this is still a inverse square law. So it is the electric field due to a point charge with respect to a fixed origin. Now let us say I have instead of one single point charge, let's say I have a collection of charges, a collection of discrete collection of charges. So in that case, what will happen? So let's say I am having charges q1, q2 and so on all the way till qn. Then what we do is we can use the superposition principle, because the electric field, it follows the superposition principle. So I take any arbitrary charge, the charge we call it as, let's say, q1, and the position of this charge q1 is qi, that's the ith charge. So we find out the position of this ith charge, which is ri prime. I want to find out what is the field at this position r. So we have ri prime, and then we have ri prime, and we have r, and the separation vector for the ith charge at this point with respect to this point is r minus ri prime. So that this charge is going to give us an electric field ei. So we find out what is this electric field ei, then we do it for each and every charge, and then we take the summation over this entire distribution. So that is like a vectorial addition of all the electric fields, which is essentially the superposition principle, and that gives us the total electric field. So we have a charge distribution q1 to qn. Then this ei, this charge is going to be this expression, so which is basically this expression itself. Okay, this expression, this is for a single point charge. So we have, instead of, we just put a subscript ei, then qi r minus ri prime divided by r minus ri prime whole cube modulus r minus ri prime whole cube, the same expression. So this is the electric field due to the ith charge, and then the superposition principle then gives the total electric field at this position r as the superposition of this, all of these electric fields. Okay, so this is the electric field due to a distribution, a discrete distribution of charges. So I'm going to end this lecture here. In the next lecture, we will show that an important characteristic of the electric field, and that is the conservative nature of the electric field, which we will see in the next lecture. Thank you.